The final topic that we'll cover is moments of inertia. What are moments of inertia used for? Principally, in structural engineering, moments of inertia are used when determining the stress in a bending member. And that's determined by the equation here on the left, where sigma is the stress, the bending stress, m is the bending moment, y is the distance from the principal axis, and ix is the moment of inertia about that axis. So this equation gives you the stress at a distance y from the axis. And you can see that it's inversely proportional to the moment of inertia. So beams with a high moment of inertia can withstand a lot of bending moment without having much stress. Now, the equation to determine moment of inertia is this integral. So looking at for the moment of inertia about the x-axis, we have the integral of y squared over the x-axis. So the more our area is located away from the x-axis, the higher the moment of inertia about x is going to be. So for example, say we had this object, it would have a given moment of inertia, but for an object with the same total area, if it was rearranged like this, then that would have a higher moment of inertia because most of the area is farther away from the x-axis. That's why I-beams are tall and slender. So we also are concerned with moments of inertia about the y-axis. And also the polar moment of inertia, which is rotation or inertia about the z-axis. And that's just equal to the sum of the other two values. So this refers to the distance from the principal axis, so the axis that passes through the centroid. But oftentimes you want to find the moment of inertia about a different axis. For example, with a composite body, say we have an I-beam, we could find the moment of inertia of this part and this part and this part all about this axis, because this is the centroid of the I-beam. So whenever we want to find the moment of inertia about an axis other than the principal axis, we can use the parallel axis theorem. And here's a figure showing the situation. So here's the area with its centroid and the principal axis x prime. But we want to find the moment of inertia about this axis, x. And that ends up being Ix is equal to Ix bar plus A times dy squared, where Ix bar is the moment of inertia about the principal axis, and A is the area, And dy is shown here. It's just the distance from the x-axis to the centroid, the distance in the y direction. And similarly, for the inertia about the y-axis, we have the moment of inertia about the principal y prime axis plus the area times the distance from the y-axis squared. So now we'll put this into practice with this example problem, where we want to determine the moment of inertia for the blue rectangle with respect to both the centroidal x prime axis and the axis x sub b, which is at the base of the rectangle. So again, we're going to use equations provided in the back of the book for the nominal inertia, or the inertia about the centroidal axis. So we have here for a rectangle, it's hard to see, but it's basically 1/12 times one of the dimensions times the other dimension cubed. And the way you choose which dimension is cubed, the dimension that goes in the direction perpendicular to the axis you're concerned with, is the one that's cubed. And the other one, the one that's parallel to that axis, is the one that's just raised to the power of 1. So here, Ix bar is the moment of inertia about the centroidal x-axis. So from our equation we have 1/12 b times h cubed. And then, so what I was saying about the direction parallel to and perpendicular to the axis, hopefully that'll be clear here. So Iy bar, which is the moment of inertia about the centroidal y-axis, that is 1/12, and then the first term is the dimension that's parallel to that axis, so it's h, and the second term is the dimension, or the dimension that's perpendicular to that axis, so b cubed. So since h is a larger value than b, well, if this figures to scale, then we can see that it'll have a higher moment of inertia about the x prime axis than about the y prime axis, because we have h cubed here and b cubed here. So now we need to determine the moment of inertia about x sub b. And the area is bh, and dy is h over 2. So that's the distance from the axis x sub b to the centroid in the y direction. So Ix is Ix bar plus bh times h over 2. So there's the equation. The main idea is that we have moment of inertia about this centroidal axis, and then to get the moment of inertia about a parallel axis, we just multiply or add in the product of the area and the square of the distance. So again, in practice, we're often working with composite bodies, which are made up of simple shapes. And the moment of inertia for a composite body is the sum of the moments of the parts. and those moments of inertia are all about the same axis. So again, going back to the I-beam example, here's a cross-section of an I-beam, and we can consider it as being made up of these three parts. And if we want to find the moment of inertia about this centroidal axis, then we have the moment of inertia of this part about this axis, the moment of inertia about this part about this axis, and the moment of inertia of this part about this axis. So the centroidal axes for these top and bottom pieces will be here, and so we'll apply the parallel axis theorem to get the moments of inertia of these about this axis. So the procedure for finding the moment of inertia of a composite body is to first sketch the parts, and label. And indicate the perpendicular distance from the centroid to the reference axis. Distances. So that's your sketch. And then the second step is to use the parallel axis theorem to determine the moments of inertia of the parts. And then the final step is to sum the moments of inertia. And like whenever we were working with centroids, sometimes composite bodies, it's convenient to work with a void or a hole, and so in that case, that has a negative value in the sum. Now we'll look at some example problems. First is fundamental problem 10.6. There are two ways to approach this composite body. We can think of it as being four separate rectangles, which is sort of how it's drawn. So what I mean is this. So here's segment 1, 2, 3, and 4. Or we could consider it to be two parts. A big rectangle and then a smaller void. So we've got part 1 and part 2, which is a hole. Again, when we are working on these composite bodies, it's good to make a table because we'll have quantities for all the different parts. So we'll go ahead and consider this to be 4 pieces. So we'll make a table. First of all, our equations that we're going to be working with, we have Ix is Ix bar plus a dy squared, and then Iy is y bar plus a d sub x squared. Okay. So we have the segment, and we have ix bar, d sub y, iy bar, d sub x, and area. So we'll find out all those terms for each segment. So we got 4 segments, 1, 2, 3, 4. Using the equations, we have for segment 1, we have 1/12, and then the smaller, so we're going about this x-axis. But we're going about its centroidal x-axis, so right here. So 1/12 times 30 times 200 cubed. Again, the one's cubed is the dimension that's perpendicular to the axis. And that is 20 times 10 to the 6th. dy, the centroid of this object is on the x-axis, so dy is 0. And iy is 1/12 times 200 times 30 cubed. The dimension now, the 200 is parallel to the y-axis, so that's why it's not cubed. And dx now is 150 plus half of 30, so 165. And the area is 20 times, or 200 times 30, so 6,000 millimeters squared. And that'll be the same for segment 3. This is 450,000. Now we're looking at segment 2 and its moment of inertia about its centroidal x-axis, 1/12, and then the dimension parallel to that axis, so 300, and then dimension perpendicular is 30 times 30 cubed, and that's 675,000. dy now is 100 minus half of 30, so minus 15, so that's 85. And I'm not considering if it's positive or negative in the y direction because we're going to be squaring it, so it wouldn't matter if we wrote down negative. And then iy, about the centroidal y, is 1/12 times the parallel dimension, so 30, and then the perpendicular dimension, 300 cubed, and that is 67.5. Dx is 0 because this centroid is on the y-axis, so you don't have to go any in the x direction. Okay, so now we can find ix1, so that's for segment 1, well 1/3 since I have the same, and that's equal to ix bar 1 plus a1 dy1 squared. So we get 20 times 10 to the 6th plus 6,000 times 0 squared. So it's 20 times 10 to the 6th. And so 1 and 3 aren't moved at all in the y direction, so their centroidal x-axis lines up with the reference x-axis. Y 1 and 3 is dx1 squared. And that is 450,000 plus 6,000 times 165 squared. Which is 163.8 times 10 to the 6th. And now for elements 2 and 4, about the reference x-axis. I'm sorry, 65.7. So 65.7 times 10 to the 6th. And then we'll again use the parallel axis theorem to get the moment of inertia for segments 2 and 4 about the reference y-axis. And we can see it's not moved any in the x direction, so that's just I bar y2, which is 67.5 times 10 to the 6th. And so Ix is Ix13 plus 2 times. Well, I'll just write it out. 2Ix13 plus 2Ix24, because we have two of them. So we have the moment of inertia of this one, which is Ix1. This one, Ix3, they're equal. Just calling them Ix13. So 2 of those plus 2 of these. And so that's 2 times 20 times 10 to the 6th plus 2 times 65.7 times 10 to the 6th. So it's the sum of the IY's, so it's 2 of these plus 2 of these, and that's 463 times 10 to the 6th. So in summary, or to review, we found we divided the composite body into 4 segments, and we wrote down the equations that we're going to be working with. And then we found the for a composite body, we're going to end up summing all the moments of inertia about a common axis. So we had the equations to find the moments of inertia for all these components about these reference axes, about x and y right here. And this is the information we need. Moment of inertia about the centroidal axis, and then the distance between those two parallel axes, and then the area for that segment. And so that allows us to use the parallel axis theorem. So a table with all that information in it, and then once we have these values for all 4 segments, then we just add them up. So here's another example, and this one will treat as a big element and then two smaller holes in that element. So this is problem 26. And we're asked to find the moment of inertia of the composite area about the y-axis. So I'm going to treat this composite body as being made up of a big rectangle and two smaller triangles that are holes. So we'll call the rectangle segment 1 and the holes segments 2 and 3. So for a triangle we have this information that's on the inside of the back cover of the book. So here's just a sketch of the centroid C and an x-axis. This dimension is B and this dimension is H. And we have that this distance here is 1/3 of H, and the moment of inertia about this axis is 1/36 times B times H cubed. So this is 1/3 H. So we have a table with the segments, and in this case we'll be using, so here's the x-axis, y-axis, so we'll work with IY is equal to IY bar, the centroidal moment of inertia, plus A times D sub x squared. So in our table we're going to need IY bar area and D sub x. Probably the worst table ever. Let me just rewrite it. Okay, so segment 1, 2, and 3. So segment 1 is a big rectangle, remember, and its centroid is located right there, and the moment of inertia. Okay, so this thing has dimensions 6 vertically and 9 horizontally. So 6 and 9. So its moment of inertia about this vertical axis, the centroidal y-axis, is 1/12 times the parallel dimension, so 6, times the other dimension cubed, so 9 cubed. And that is 364.5. And it has units of inches to the 4th. And its area is just 6 times 9. And the distance dx is the distance from the reference axis to the centroid, so that's 4.5. Segment 2, so its centroid is located about right here, 1/3 of the way, and so its moment of inertia about this axis, this centroidal axis, is 1/36, and then parallel dimension, so that is 3. This distance here is 3, and then the other dimension, so that is oh, okay. I have this drawn badly. It's not to scale. It looks like, so here's actually the middle. There's 4.5. So this kind of looks like it goes to the middle of the rectangle, but it's not. So anyway, this dimension here, what I'm getting at is this is 3. It's not half of this. So times 3 cubed. And that's equal to 0.75. And its area is 1/2 times 3 times 3. So 4.5. And the distance from the reference axis to the centroid, or to this parallel axis, the centroidal axis, is 1/3 of 3, so it's 1. And the final shape, its centroid is located over here. And there's the parallel axis. So that is 1/36 times this parallel dimension, which is 6, times 6, and then the other dimension, which is also 6. And that's 36. Its area is 1/2 6 times 6, so 18. And dx is 3 plus 2/3 of 6, so plus 4, so that's 7. And now we have all the information we need to find out the moments of inertia of these segments about the y-axis. So go ahead and make another column in this table. So that's, this one is 364.5 plus 54 times 4.5 squared. So that's 1458. And now we have, for the next segment, 0.75 plus 4.5 times 1 squared, and that is 4.5. No, that's 5.25. And finally, 36 plus 18 times 7 squared, 918. Okay, now we come to our summation, but the important thing to remember is that these are voids, so they're negative. So the moment of inertia of the composite body is 1458 minus 5.25 minus 918, and that is 535. That's inches to the 4th. And I won't complete the next example. I'll just get it started, and then I'll leave it up to you because it's really the exact same as the one we just did. So here's the problem, and we want to find the moment of inertia of this about the y-axis again. So we're just going to use this equation to find the moment of inertia of the different components making up this composite body. So we'll have to get all this information, the centroidal moment of inertia, or the moment of inertia about the centroidal y-axis, the area of the segment, and then the distance between the two parallel axes, that is the centroidal y and this reference y. And so here's how I look at the figure. So we've got a rectangle, and then again 2 voids. So there's one void, and here's another void. It's poorly drawn again. So we find the moment of inertia of this segment about the reference y-axis. Moment of inertia, and then subtract the moment of inertia of the circle about that axis and the moment of inertia of the triangle about that axis. So we've got, the only thing new is that now we have a circle And so we'd have to go to the back of the book and look at this equation for the circle. And that gives us the moment of inertia about a centroidal axis. So, to review, the moment of inertia is important in one application of bending stress. And moment of inertia is greater. It's determined about an axis, and it grows the farther the area is from the axis. And we can determine the moment of inertia about the centroidal axes for these simple shapes using the standard equations, and they're copied in the back of the book. And then if we want to find the moment of inertia about a parallel axis to that, we use the parallel axis theorem. And then for composite bodies, we can sum these moments of inertia as long as they're all about the same axis, which is what we've done in this example.